Hi everyone, my name's Alex. I'm an engineer and my passion is with design, development and prototype production of all sorts of engineering solutions. Welcome to episode 2 of this 4-part video series on welding distortion. In this episode we'll take a closer look at the magnitude of the internal stresses which develop in our workpieces due to the local welding heat, or any other local heat if you will. Also, we'll discuss in more detail why these stresses develop at all, why they reverse upon cooling, and why they can cause even more distortion with post-weld machining or post-weld heat treatments. So let's take a look. Well, the experiment of this episode is a 3-bar truss, of which the central bar gets heated and then is left to cool. This represents a simplified case of welding. Think of the truss as our workpiece and think of the central bar as the place where we currently weld. Our sample is out of 5mm S235 mild steel. This truss is a common textbook example, frequently used to explain the principles of welding distortion. But the textbook explanations I read so far always leave some questions unanswered. That is why we will conduct this experiment with the help of a mechanical strain gauge, and then we'll interpret our observations with the help of this contraption here. I know it looks funny, but I designed and built it in order to visualize of this experiment what is invisible to our 5 senses. Nice about this 3-bar truss is the effect of these 2 slots here. They greatly simplify the problem in comparison to our previous experiments. As we heat the central bar here, the heated spot's expansion is constrained almost exclusively in this direction by the 2 outer bars which remain cold. Expansion of the central bar in width or in thickness is almost unconstrained. In other words, the 3 bars experience exclusively tension or compression in this direction and almost nothing else. The resulting stress pattern in the bars is called uniaxial, while the stress pattern in the previous experiments of episode 1 was of a radial nature. The 3-bar truss experiment compares more or less to a segment of a welded corner joint, like so, while the experiments of the last episode compare more or less to a segment of a welded butt joint. But nonetheless, the distortional mechanism involved is the same. The 2 slots are sized in a way so that the width of the 3 bars is equal. This is not a necessity, but it simplifies the problem even more. Since we do not apply external forces to the truss, the bar's forces in this direction must balance. For this reason, and because of symmetry, we know that the stress in the central bar equals -2 times the stress in the outer bars. In other words, if we have 10 units of tension in the outer bars, the central bar experiences 20 units of compression. Before we start the torch though, let me say a few words about this mechanical strain gauge here. It is a quite antique instrument, not much used nowadays anymore. But for the purpose at hand I like it very much because it's very dependable, intuitive and easy to understand. Think of it as a high precision dial indicator with knife edge pickups here. It is clamped to our sample with the screw down here, like so. Let me just sit this down here and bring you in a little closer. The purpose of the knife edge pickups here is to pursue the deformation of discretely defined points on our sample, not to contact the whole area which gets strained itself. This one knife edge here is integral part of the instrument's body. This other one, however, is hinged in the instrument's body around this secondary knife edge back here. And if you look closely, you'll see that it is actually a lever which ends here. The lever's displacement here is transmitted to this second lever, or rather the indicator needle, which is hinged back here. So basically we have two levers which magnify the displacement between the knife edges here very much. This particular instrument is scaled so that 1 micrometer displacement between the pickups equals 1 indicator division. As I release the indicator needle, you see we have to zero it with the aid of this very fine pitch screw back here, which simply displaces that hinge. Set it 0 again. Let me just rest this down a little. And to give you an idea of the sensitivity of this gauge, see what happens if I bend just slightly on the sample. And remember, this is 5 mm thick material. This also helps us to ensure that we interpret the scale right, so this direction is obviously tension, whereas this direction is obviously compression. I took the liberty and made a custom scale, which should go on here like so. And this scale shows at which strain this particular material starts to yield, in other words, to deform plastically. There is a duplicate indicator on the other side of the instrument, which we don't need for our purposes. Both indicators in conjunction can be used for identifying errors like bending in tensile test samples, for example. But that's another story. Okay, the strain gauge is set. And zeroed. Should work fine. But let me add another thing which I almost forgot in the introduction. I made sure that the flat stock out of which this 3-bar truss is perfectly free of residual stresses. You can never be sure about this, particularly if you're dealing with cold rolled material, but I normalized this flat stock material in the vacuum furnace prior to this experiment here. Now let me just slide in this very exquisite heat shielding here before I fire up the oxyacetylene torch. I hope you will be able to see the indicator all the time while I'm heating the central bar here. Keep an eye on the indicator and keep in mind that we started at 0. I now heated the central bar to an orange red, and our maximum reading on the outer bars is approximately almost 60% of the yield strength of the material. This in turn means times -2 that the central bar is loaded with approximately almost 100% or a bit more than 100% of the yield strength of the material. So obviously this material has a little more strength than in the data sheet, but nonetheless. Explained in other words, the heated spot is now thermally expanded. It can expand in width and thickness direction of the bar quite freely. That means free of stresses. But the expansion in length direction here is something the outer bars don't like. They constrain it by compressing the central bar. The outer bars, in turn, get pulled apart by the central rod's expansion in length direction. This behavior has a certain balance, which is controlled by the bar's cross-sections. But now, let's watch what happens during cooling, and for this I'll speed up the video. Well, the 3-bar truss now has almost entirely cooled. But interestingly, and that's important to note, our strain gauge indication is not back at 0 where we started from. So if we can trust the strain gauge, the outer bars now experience residual compression stress of almost 20% of the material's yield strength. This in turn means times -2 that the central bar now experiences almost 40% of the material's yield strength in tension. That's quite a lot, isn't it? So you see that during cooling, the stresses in a given bar reversed from tension to compression or vice versa. And obviously, we've created substantial residual stresses in this workpiece just by heating it locally. And the same thing continually happens in welding. If you recall, in the last episode we found out that local heating caused thickening of a sheet sample. The analogon we used to explain this behavior was the rising cake in the cake tin. Let's see what happened with the heated central bar. So thickness now is 5.23 millimeters and width of the central bar is 20.28 millimeters. Off camera I noted the initial cross-section dimensions of the central bar. They were 5.01 millimeters in thickness and 19.96 millimeters in width. After the experiment we found a thickness of 5.23 millimeters and a width of 20.28 millimeters. This equals to a thickening of 4.4% and a widening of 1.6%. In contrast to episode 1, we also find a widening here because the central bar is not constrained in width direction. Or you could say because we have an uniaxial stress pattern here, not a radial one. Our cake here did rise both in thickness and width because the cake tin did constrain it only in length direction. Next, let me prove to you that the 3-bar truss now really is loaded with severe residual stresses. According to our strain gauge, the outer bars are compressed in length direction pretty strongly. We can validate this with the hacksaw. I think the tight pinch on the saw blade does clearly highlight the compression of the outer bars. Some of the previous contents of this episode you can also find in textbooks. But a question that always bugged me is still unanswered. Obviously, the central bar plastically deforms during heating, which shows as thickening and widening. But why does this process not reverse as the workpiece cools? Why doesn't it just deform back? Why, instead of a back deformation, do develop those high residual stresses? This question, in my opinion, is key to understanding welding distortion. Let me try to answer this with the aid of the contraption here. The individual parts of this contraption each represent part of the 3-bar truss's mechanics. The central spring here, for example, represents the elastic behavior of the central bar. That means we can see mechanical stresses in the central bar in form of compression or tension of this spring here. Similarly, the outer springs represent the elastic behavior of the outer bars. The connection up here represents the truss's connection here. This here is just a guide pin along which the connection can freely slide. Then we have this frictional element here. This frictional element represents plastic deformation of the central bar. This screw here can be tightened or loosened to give higher or lower friction in order to simulate higher or lower yield strength of the central bar. Also, I can lock the frictional element with this pin here in order to simulate material with infinite strength. The colored lines up here serve to show displacement of the frictional element, like so, which represents plastic deformation of the central bar. And the actuator here represents heating and cooling of the central bar. So first, let's simulate a 3-bar truss with infinite strength. This is a purely theoretical case, but it helps to understand the realistic one. Infinite strength means no plastic deformation. Therefore, I locked the frictional element. Now, as we heat the central bar, which I simulate with the actuator here, you immediately see that the central bar gets compressed, while the outer bars are stretched. This means compressive stress in the central bar and tensile stress in the outer bars. Let me bring you in a little closer and keep an eye on this point here. Also, you see that the truss becomes longer. But since no plastic deformation occurs, all of this reverses as the central bar cools. When the central bar has fully cooled, we are back at the same configuration which we started from. No stresses in all the bars. Even though this case is purely theoretical, it would be nice if our welded workpieces would behave that way. No residual stresses and no distortion. But the real world is different. Next, let's simulate another purely theoretical case. A 3-bar truss with almost zero strength. Nobody would want a workpiece with zero strength, but again, this case serves to understand the realistic one. To simulate zero strength, let me remove the locking pin and let me fully open the screw of the frictional element. Now, as we heat the central bar, you can see that it immediately deforms plastically. Also, since we have zero strength, the bars experience no stresses. And what's important here is that as soon as we start to let the central bar cool, you see that the plastic deformation of the central bar reverses. After cooling, similarly to before, we are back at the same configuration which we started from. No residual stresses and no distortion. But again, the real world is different. Well, materials with infinite strength do not exist. And on the other hand, there is no point in making workpieces with zero strength. So the previous two cases are extreme cases and are just academic. In reality, we are somewhere between those two cases. We work with materials which have a certain strength and usually are capable of plastic deformation. So let me set the frictional element to a certain strength. A little looser. And let's see what happens in a realistic 3-bar truss. As we heat the central bar, first the same happens as in case 1. Compressive stress in the central bar and tensile stresses in the outer bars develop. But as we reach the strength of the central bar, which is about to happen right now, plastic deformation sets in. From this point on, the stresses in the bars don't grow much more, but rather the plastic deformation in the central bar continues to grow. As we start to cool, the stresses diminish. Therefore, plastic deformation doesn't grow anymore. At this point now, the stresses in the bars have relaxed. But our central bar is not completely cool yet. As it continues to cool, you see that the stresses reverse. Since the central bar is shorter now because of plastic deformation, it starts to experience tensile stress. The outer bars begin to experience compressive stresses. The stresses grow until the central bar is fully cooled. And you see, our truss is now loaded with residual stresses, just as we observed before on the real truss with the strain gauge. There are cases in which some reverse plastic deformation takes place upon final cooling, like so. But even if so, this is only a little part of the main plastic deformation and only plays a minor role in the whole distortional theater. I brought you in a little closer on the springs. Let's repeat the process and keep an eye on this mark up here where we started from. So starting to heat, plastic deformation sets in, starting to cool, point of relaxation, cooling further, and finished cooling. So one thing very important to note here is that our workpiece has become shorter. This is one form of distortion and a natural result of the shortening of the central bar. Shortening of welded workpieces is a very common occurrence, particularly noticeable in cases of large or long structures with many welds, such as welded airplane fuselages or frames. Shortening can give quite some trouble with welding jigs, in which the workpieces get more and more stuck as welding progresses. If you recall that the hacksaw got stuck in the outer bar earlier, this clearly shows why. The outer bars are compressed, and if we cut a slot through them, the slot tries to close on us. And this brings us to the last point of this episode: springing back distortion of welded workpieces due to post-weld machining or post-weld heat treatments. Recall that our welded workpieces are in certain areas loaded with residual stresses, for example like the contraption here. If we machine away material which is loaded with residual stresses, let's assume we machine away part of this bar here, see what happens. I can take off the holder of the spring here. There's a pin in there. The truss experiences bringing back distortion because the remaining residual stresses must find a new balance again. This is only possible if the workpiece distorts. Similarly, our welded workpieces distort if we conduct a post-weld heat treatment. Typically what happens during heat treatments is that material loses strength as it gets hot. We can simulate this with decontraction by loosening the screw here. As I do this, you see that the residual stresses relax a little, which in turn causes bringing back distortion, here in form of lengthening of our truss. A better term for this would probably be relaxation distortion. There is no bending in this case because our truss is symmetrical. It doesn't matter much if we stress relieve anneal, solution heat treat, normalize, or whatever heat treat our workpiece, as long as the temperature is high enough. Bringing back distortion simply occurs in the oven or while the workpiece is hot. Well, so far for episode 2 of this video series. In the next episode we'll take a look at flame straightening, which you can consider as producing on-purpose distortion. Well, thank you very much for your interest in this video. I appreciate your time. All the best for your welding projects, and thank you.